Okay. In this video, I'm going to look at two very closely related topics, the average rate of change of a function and what's called the difference quotient. It turns out that both of these things, the average rate of change of a function and the difference quotient, are really just slight variations, different perspectives on one concept, and that concept is closely related to slope. The slope of a line, you'll recall, is the difference of the y values for that particular line, or for a particular point on that particular line, let's say, divided by the corresponding difference of the x values on that particular line. Again, for a point on that particular line. My words are not coming out exactly the way I would use. So we have 2 points, x of 1, y sub 1. It's on the line. X of 2, y sub 2 is also on the line. And we're looking at the ratio of the differences of the coordinates of those points. Now, math is a language where we try to say a lot with as little effort as possible. So instead of y sub 2 minus y sub 1, sometimes we replace it with this delta notation, delta y, which I have here. And so you could rewrite the slope as delta y over delta x. Delta y, delta comes from d for difference, but it's also referred to as a change. Often a small change, but not necessarily. But it's pretty common in physics and in mathematics to represent a change of a quantity as this delta to express the idea that we're talking about how we went from one thing to another thing. So 2 different energy levels, for example. If the energy of a system changes from one state to another state, that change of energy might be delta E. Okay, cool. So coming back up here, if we use the idea that y is really the same thing as the function value, f of x, you could, of course, also call it delta f, or as I put it up here, delta f of x. So those are just different notations for the same idea. And that's part of learning any language, is getting used to the synonyms, so to speak, the fact that there might be a different sort of emphasis, but pretty much the same idea. Okay, so as mentioned, x sub 1, y sub 1, x sub 2, comma, y sub 2, those are specific points. And just a generic point on a line or on a curve is labeled x, comma, y. So if you were to look at the graph of f, all the different points are just have generic labels of x and y. Now, the reason to bring that up is because what we're going to do is look at a slight change in notation here. Delta x, again, was the difference of 2 particular x values, but we can also use it from the point of view where we're talking about a completely generic point where we don't care what the coordinates are, and then we have some other point that we're considering at the same time. So in that context, we might call the generic point x, comma, y, as I have here, and the specific point, well, then we could go ahead and bring in the x sub 1 and the y sub 1 to refer to that. So we don't have 2 specific points, we have 1 completely general point and 1 specific point. It's really common for reasons that I don't want to spend too much time talking about. It's really common to replace delta x with this letter h here. And if we do that, then we have h is equal to x minus x sub 1. Now it turns out that You could also switch that around and call it x sub 1 minus h, and it would be the difference of two values. And depending upon the context, either one of those works, but the notation I've got here is the one I'm going to be using here. So our x sub 1, well, if we rewrite this equation and solve for x sub 1 in terms of x sub 1 added to both sides of the equation, well, that doesn't look right because the h, of course, then should show up as negative over here, but it actually is right because, as I was saying, it doesn't matter what order you do this in x minus x sub 1 minus x, because it's always going to be corresponding with the function values, the y's, and if you change the order for the x's, you change the order for the y's, and the negatives cancel out in that. So sometimes can get lost in that h here, and if I wanted to change it to negative h, it wouldn't necessarily be wrong. We just don't. Truth of the matter is we don't know whether h is positive or negative anyway. It is sort of another generic thing that's going to show up here. Okay, so a lot of words. X sub 1 equals x plus h. Take my word for it, it makes sense. If that's true, then it would follow that y sub 1, should actually have a label here. Let me change that, fix that. Y sub 1 would then be f of x plus h. Now it turns out that we can switch the roles. Kind of what I was talking about here is the fact that you can switch the roles of the x and the x sub plus x sub 1 around. And so that's some of the possible confusion that can happen with the sign here that I was discussing. Okay, so here we've got it all over again, where I actually had gone and fixed this part of it. And the reason for that, duplication. So I can get rid of that now. Is we can now call this thing by the name difference quotient. The difference quotient is the same as the average rate of change of the function that I was talking about before up here. Because, well, if x sub 1 is x plus h, then the denominator here is just x minus x sub 1, which gives you just h, or negative h, as the case may be. And the y's likewise will line up in the same sort of way. So what we have here is a difference of y values, difference of x values. Like a lot of things in mathematics or any language, you don't want to overstress on things that might be a little bit confusing. Just sort of make note of it and say, okay, this seems kind of weird, all this terminology, all this symbolism. As you get familiar with it, it will make more sense. Now, the key idea here is this really is the starting point to calculus. And being able to work with this notation, to be familiar with it when you get into calculus, is going to be a lifesaver to you. So whether we're talking about looking at it from the perspective of y sub 2 minus y sub 1 over x sub 2 minus x sub 1, which is the typical notation for the slope, or whether we're talking about the average rate of change of the function or the difference quotient, they're all referring to the same thing. I'll look into some of the algebra in the next video about how you can manipulate the difference quotient and calculate this thing. But for now, I want to look at what this geometrically means. So we'll change to a different window here and look at a specific function. So I've got a parabola here. The parabola is the graph of y equals 0.2x squared plus 3x. And so we have a particular point here that I'm looking at. I call it a particular point, but let's actually just think of it as being x and y. It has an x-coordinate close to -6 and a corresponding y-coordinate of about -10.8. But that doesn't really matter all that much. It's just point A. We have two other points here. Point B, I think this one is. You can't really see the label on it, but I believe this was point B at about -1.5, and y is negative for x and the -4 for the y value. So that's point B. Now, if we're talking about the parabola here, a line that cuts through 2 points on the parabola is sometimes referred to as a secant line, S-E-C-A-N-T. If you've taken any trigonometry at all, you've run across that term secant, and originally it just refers to a line cutting through a curve, most typically a line cutting through a circle, through 2 points of the circle. Well, if we imagine that this point is x, comma, y, then this point would be x plus h, comma, f of that x plus h. The y value would be f of the corresponding x value. And so we're relating this point to that point by throwing in that h. So that's the whole idea of the h. If this is x for the x value, then this is x plus h for the x value. And what we do is we let h become smaller. Well, if h becomes smaller, since h is the difference of this point and that point, it follows that if h becomes smaller, this point will get closer to the point we started with. So it might move to this point here, for example. Point C, which has coordinates of about -3.4, and the y value is close to -7.9. But we can just see visually that this point is closer to that point A than point B was. And then we have another secant line cutting through those. The slopes of the two lines are different. The first secant line has a positive slope. The second one likewise has a positive slope, but it's not as steep. And it turns out that if you were to go ahead and just let these points march closer and closer to the point we started with, you would eventually reach a stage where we would get a line which is tangent to that. So a tangent line would have a slope in this particular case. Let me do a quick calculation. So it's 0.2, so we're looking at 0.4x. What was it looking? Plus 3. So if we were to look at with the x value about -6, so that means that the slope of the tangent line should be about 0.6, I believe. So if we were to go ahead and input, well, I don't know the y, I'll just go ahead and create that. So I'm going to make a tangent line, so it's going to touch here. And the idea of the tangent line is it touches the curve at that particular point and doesn't touch the curve anywhere else. In this case, anyway, that's not always true. It's frequently true. Depends on the nature of the curve that you're starting with. Well, I can't really visually see exactly what that is, but the slope should be about 0.6, which means if I go 1 unit to the right, I go up about 0.6 units. So 1 unit to the right would be about here and go up right about like that. So pretty close to that line there. It's tangent to the curve. And then in calculus, what they do is say, well, if you were to go ahead and zoom into that point, calculus was originally invented. So instead of working with the parabola, which is curvy, we can work with a line which in the neighborhood of this point is not curvy. So you can use a linear model to represent the parabola. And you'll see this when we zoom in here, it's really kind of hard to even identify the parabola from the 4 different curves that we have here. the tangent line, the two secant lines, and the original parabola. Which, where is it? There it is. Okay. Okay, so we'll look at some of the algebra of the difference quotient in the next video. This is just sort of an introduction to a very important concept and one that's worth looking at in another 2 or 3 videos to come.